We're going to determine if the series, the summation n equals 1 to infinity of 1 divided by n squared plus 5 converges or diverges. And we're going to do it by using three different methods. The first method we'll use will be the limit comparison test, LCT. The second method we're going to use will be the direct comparison test. And we'll call it CT. And the third method will be the integral test. And I guess we can call that the IT. So this problem, the reason for this video is to show that in some of these series we can use more than one method, and some of them even more than two, to arrive at the same result. So we'll start with a limit comparison test. We have our series, the summation n equals 1 to infinity, 1 divided by n squared plus 5, and we're going to call this the a sub n series. And we need to select the b sub n series to compare it to, and that same series will be used for the comparison test and the limit comparison test. The way we do that is we look at the highest power of n in the denominator, in this case it's 2, and the highest power of n in the numerator, that's 0, subtract n from d, that gives us 2, and we're going to select the simplest series so that the difference in the highest powers, denominator minus numerator, is 2, and we'll call it our b sub n series. So in this case the selection is the series n equals 1 to infinity, 1 over n squared. So now let's evaluate the limit as n goes to infinity of a sub n divided by b sub n. Remember, when this limit is, call it L, if it is positive and finite, both series converge or both series diverge. So this is the limit as n goes to infinity, 1 divided by n squared plus 5 divided by 1 over n squared. So that's limit n goes to infinity of n squared divided by n squared plus 5. Since the highest powers of n in the numerator and denominator are the same, the limit will be the ratio of the coefficients, 1 divided by 1. So our limit L is equal to 1. And remember, when L is positive and finite, both series either converge or both series diverge. So the series summation from 1 to infinity, 1 divided by n squared plus 5, and the b sub n series, n equals 1 to infinity, 1 over n squared, behave the same way as far as convergence or divergence. Well, since this series is recognizable, this is a p series, and p is equal to 2, we know that this series converges, and therefore we make the conclusion that this series also converges by limit comparison test. Now, to use regular or direct comparison test, we note that n squared plus 5 is always bigger than n squared, and this is for any n greater than or equal to 1. Since the left hand side has n squared, so does the right, but the left hand side has also an extra 5 added every time. Now, by using basic algebra, if we put these in denominators, 1 over n squared plus 5, since that's a bigger value, is less than 1 over n squared, and this is again for n greater than or equal to 1. Now, when we sum these up, the summation n equals 1 to infinity, 1 divided by n squared plus 5. Clearly this is a positive value, so it's either a finite positive number or it's infinity, clearly greater than 0, but it's also less than the summation n equals 1 to infinity of 1 over n squared. Now again, we recognize this series. This series is p series. With p equal to 2, it converges. So in other words, all these values 1 over n squared for every n from 1 to infinity add up to finite number. This series cannot be infinite. It cannot add up to infinity because it's bounded above by a finite number. So it's forced to converge. This series also converges, and this time the reason by just direct comparison test, which we'll abbreviate by CT. And now let's use the integral test. Remember the integral test. We take f of x to be the function 1 divided by x squared plus 5 defined on the interval 1 to infinity. Well, this function is clearly continuous. It is differentiable because we can easily differentiate it. And it is decreasing because the numerator is always 1. And as x gets larger and larger and larger, so will the denominator, making the function smaller and smaller and smaller. In addition to that, if we plug in positive integers for x, we end up with the nth term of our sequence that gives us the series, which is 1 over n squared plus 5. So integral test applies, and when we integrate from 1 to infinity of 1 divided by x squared plus 5, if this integral is finite, if it converges, so does the series, and if the integral diverges, then the series will diverge as well. Let's recall that the antiderivative of a function that looks like this, x1 divided by x squared plus a squared, is 1 over a times inverse tangent of x over a. Well, here our integral looks exactly like that, with a squared being equal to 5, so a is the square root of 5, and therefore the integral from 1 to infinity of 1 divided by x squared plus 5 is equal to 1 over square root of 5 times inverse tangent of x over square root of 5, and that's evaluated from 1 to infinity. And using limits, this is equal to the limit as x approaches infinity of 1 over the square root of 5 times inverse tangent of x over square root of 5 minus 1 over square root of 5 times inverse tangent of 1 over square root of 5. Well, let's look at this limit. As x goes to infinity, so does x over square root of 5. And all we have to do is look at the graph of inverse tangent of x. It looks like this, with this line here, this horizontal line being at the pi over 4 level. So in other words, as x becomes larger and larger and larger, inverse tangent is heading toward pi over 4. Therefore, this is equal to 1 over square root of 5 times pi over 4 minus inverse tangent of 1 over square root of 5. This is clearly a finite number. Therefore, the integral converges. So we'll line these up. The integral from 1 to infinity, 1 divided by x squared plus 5, converges, and so does the series, the summation n equals 1 to infinity, 1 divided by n squared plus 5, and this is by the integral test. So we're able to show that this series converges by using 3 different tests that we have learned